This time we're talking about acids and bases, and what we want to do is start with what we know from previous courses and move ourselves a little bit forward. So one of the things we've already done so far is we've learned how to recognize an acid. We did it with nomenclature, where an acid starts with a hydrogen. Hydrogen with something else can be named as an acid. And we've got different ways of naming the acids. That's not what we're really worried about today. However, make sure you know how to do that. In previous course, you probably talked about the properties of an acid, where an acid is something that tastes sour, an acid is something that has a low pH, and an acid is something that you may have said that an acid is a solution, or comes from a solution where you take a non-metal oxide and you dissolve that into water. Maybe, maybe not. What we're going to be focusing on is what's called the Arrhenius definition, proposed by savant Arrhenius, who said that an acid is a compound that increases the concentration of hydronium ion in water. Now, hydronium ion is H3O+, it's what's in the square brackets, and the square brackets is a notation that we use to say concentration of. So concentration of hydronium ion is the square brackets H3O+. That's something that you need to know. That definition is something you need to know. And we do have a lot of sour foods that are acidic, or acidic foods are sour, although I do want to point out that anytime you are defining a chemical in terms of its taste, you're setting yourself up for a bad science day. But off we go. Bases, we haven't really spent the time recognizing them because we didn't do a specific nomenclature of it. However, bases typically end in hydroxide, OH. Not exclusively, and there's other compounds that have basic properties that don't end in OH, and there's OH compounds that don't have basic properties, but we're going to kind of work around that because we're going to focus on this course. You may have said that bases had things like a bitter taste. You may have said that bases had a pH of greater than 7. And you may have learned that bases come from metal hydroxides. So you take sodium oxide, dissolve into water, you'll get sodium hydroxide. And Arrhenius said something about bases, that bases were compounds that increase the concentration of hydroxide ion in water. And there again, square brackets around my OH with a 1- ion charge, it means concentration of hydroxide ion. Okay, you know how everyone's pretending to like kale right now? Kale has a bitter taste that we generally don't like. So does broccoli. Fun fact, some people have a genetic mutation that gives them, well, it's not the greatest superpower going, but they're called super tasters. But super tasters sounds awesome, but all it really means is that broccoli tastes extra bitter for them. So hard pass on that superpower. But coffee also has a bitter taste, which some people like, some people don't like, some people get used to, some people dump sugar in it, things like that. And also dark chocolate has a slightly bitter taste, which some people like, some people don't, but it comes down to the compounds in them that have basic properties like the bitter taste. You've probably seen a pH scale. If you haven't, here it is. If you need more than that, we'll eventually come back to it, so I'm not going to worry too much about it right now. I do want to point out, though, that the 0 and 14 are not limits. You may have heard that before. The pH runs from 0 to 14. Not true, although most solutions do fit somewhere inside of that. But you can have pHs that are outside of those start and end points. So they're not really start and end points. They're just numbers that we have. We need to take a closer look at Arrhenius, though. That's not what I mean. Can we? All right, thank you. Arrhenius also talked about the dissociation of acids. Now, if you go back to that definition, it said that something increases the concentration of hydronium ion, but there's no hydronium ion in an acid. There's a hydrogen. So how do you get hydronium from hydrogen? Well, you start out by taking that acid and breaking it apart. You dissociate it, take it apart, split it. And then that H+, which if you think about it, hydrogen ion is a proton. A hydrogen atom, 1 proton, 1 electron. Take away the electron, you're left with a proton. So an H+ is a proton. That is really reactive, and it reacts to the first thing it can find, which in this case is water, and it becomes a hydronium ion. So I can simplify that whole operation by writing acid plus water is hydronium and whatever other ion is. And as I change up the acid, I'm going to change that other ion, but I'm not really going to change much of anything else. Acids are going to dissociate more or less than each other. I mean, they're either going to dissociate all the way or less than all the way. And that is going to be key. Okay? So what we know about how acidic something is depends as much, or it depends a lot on concentration, but it depends even more on strength, how much it dissociates. So now we talk about strong acids. Now I want to emphasize that strong acids is not the same thing as concentrated. You can have a dilute strong acid. Sounds a little bit weird because we want to think that those two things, strong and concentrated, mean the same, but they don't. So when somebody complains about the coffee being too strong, A, they're wrong. B, it's not strong, it's concentrated. You can correct them. Tell them I said so. But strong acids dissociate 100%. And what that means is when you have an acid molecule, strong acid molecule in water, or a whole bunch of those strong acid molecules in the water, every single one of them breaks apart. None of them are left. These are the 6 strong acids. Yes, you need to know the 6 strong acids. Okay, what does that mean? Well, basically what it means is what I put on the label isn't actually true for what's in the bottle if I'm calling it a strong acid. So I've got 3 acids here that you may see a label for something like that. But what it actually means is that I've got that number, that concentration of hydronium, because the acid dissociated 100% into hydronium and other ion. And every single time, it doesn't matter what the concentration is, the concentration of acid will actually be 0. The concentration of hydronium ion, the thing that makes an acid, will be whatever number. Now that's only true for strong acids. If it's labeled for a weak acid, this doesn't work and I need more information. Okay, what about weak acids? Well, they don't dissociate 100%. Now I know you might be thinking that's really unfair for the 95% dissociation acids, but the good news is there aren't any of those. Many of the weak acids are less than 5% dissociated, so there's this huge gap between how much a weak acid dissociates and how much a strong acid dissociates. So we don't really have to worry about middle of the road. We don't have to worry about fuzzy gray lines between when is it weak and when is it strong. It's a pretty clear line. In solutions, a similar thing starts to happen. The difference is most of the molecules, instead of dissociating or reacting with water to form hydronium and the other ion, most of the original acid molecules stay as original acid molecules. They don't dissociate. And that's going to change a lot of things. Okay, what about bases? Bases are actually going to be kind of similar in a way. I can recognize a base from what it contains. It contains a hydroxide. Now that's true for several of them, right? There are several compounds that we know to be bases that have hydroxide in them. But the thing about hydroxide-based compounds, or compounds that contain hydroxide, is a lot of them are not very soluble. So if I think about an iron 3 hydroxide or a calcium hydroxide, not super soluble. So I wouldn't really be able to get much of a solution of base using them. But there are also compounds that don't start out looking like they'll be bases because they don't contain hydroxide, but then they do react to form hydroxide ions. So in the case of ammonia, okay, it can do that. So you can have strong and weak bases as well. Now for us, the strong bases are going to be metal hydroxides, keeping in mind that some of them don't dissolve real well, so it's a really small list. I'll give you a list at some point if you need it of these are the ones that are considered to be strong. Pretty much it's group 1 hydroxide, sodium hydroxide, potassium hydroxide, things like that. Weak bases, if you see nitrogen-based compounds, nitrogen-based bases, those are going to be weak. Okay? So ammonia is going to be the one that we use. Okay, so hopefully that was enough to move us forward, but you should be able to recognize an acid and a base, and you should be able to recognize which ones are strong, which ones are weak, particularly for the acids. That's really where we're going to spend most of our strong, weak focus on things. Anyway, we'll talk to you another time.